if we have sum of differentiable functions, then we know that if this the number of functions in this sum is finite, then we can take the derivative of this sum equal to the derivative of each term. This is not always the case for infinite series. However, for this type of series, the following result states that this type of series can be differentiated term by term in the convergence domain. What does this mean? I'm going to give you one example of this, and then you understand it. It's very easy to see how this can be applied. So let me show you this example. 1 over z is a very easy example. And we have seen before that if we want to find the Lorentz expansion of this function around the point 1, then we do the following trick and realize that 1 over z is just this geometric series. So we know that z to the power of minus 1, or 1 over z if you like, is just equal to this expression, this series. Now I just let the counting variable go from 1 to infinity, just to not get any problem when n is equal to 0 here, because we are going to differentiate it eventually. So we are starting with the constant value appearing when n is equal to 0, and this gives the first element 1, because minus 1 to the power of 0 is 1, and z minus 1 to the power of 0 is also 1. Then we have the remaining terms like this, starting from n equal to 1, from 1 to infinity of this guy. If I now want to find the series, or the Lorentz series for the derivative of this function, I just do know the following. I take the derivative of this guy is just equal to minus z to the power of minus 2, and I differentiate this term by term. This is just a constant, so the derivative of this constant is of course 0, and the derivative of each of these terms are, using the same rule as I did for powers of z, I obtain that this is just n times, the derivative of this guy is just n times z minus 1 to the power of n minus 1. This is the usual formula for the derivative of this function. So then I obtain that minus z to the power of minus 2 is just equal to this series. So this must be the the Lorentz expansion of this function.